Oh, go ahead.
Julia is clearly going to be the next director, not only chair training, but laser training.
Or the ELKA specific training.
Oh, right, yes.
I think we don't want this. Okay. Good morning, everybody. So I will talk about, and it's a relatively informal talk because I will show some really new results which we have to stimulate some discussion. And I will cover quite some topics, but everybody's an expert. I don't need a lot of introduction there. So we'll talk about what we have been doing lately on collinear, unpolarized PDFs, and I will give a summary on the polarized PDFs, and also what we are starting on fragmentation functions. And we'll at the end have a couple of a list of questions which I think we maybe want to answer before an ERC comes, for theoretical and also experimental. And also work, of course, isn't done by me. It is done by a linear mixed combination out of Ignacio, Shoshun, Charlotte, Rodolfo, Hubert, Marco, and Katharina Wichmann lately, because we are kind of getting involved in X-Twitter, where we have also some other projects which we want to do on the ground. So, the inner life of hadrons, the pattern distribution functions. Nice plot from Hawaii I was last year, which you see the different colors. So, okay. Color and the inner life of
Hawaii.
Yes, exactly. Okay, so there is an enormous wealth of data which are used in the NNPDF 3.1, and that is the latest, to constrain the unpolarized PDF. So the HERA, the Tevatron data, the fixed target data here, and of course now also data for the LHC. But still there are quite some areas, and I will show this, where we have basically very little knowledge about the PDFs, and the strangeness is one of them. So here that is NNPDF CT4 and MHT14, which is 14, where you see actually the uncertainty for in next to leading order on S, and here you see it on the ratio of S and S bar to the light close. And you see low X, and the X is not even so low, so actually low below 10 to the minus 2, and of course also at the high X, we basically have no knowledge about the strangeness.
How come the neural network is much smaller than the...
Here, it depends on which data sets are included. Some of them, so the NNPDF just came out 2017, so it probably has some of the W data and the W to C ratio data in from the LHC, which were not yet available for CT14 and also for this one. And it's right, the X range also where they are sitting. So I think that is a consequence of the data sets, because people publish it, are never exactly the same. If you do this LHPDF, also PDF for LHC, they kind of do this where they benchmark against each other, and I didn't pick a plot from there. I just took this one. I don't think the conclusion is very different. So there's also has been work by Alberto and collaborators actually to look into some constraints on the inclusive, and we want to redo some of it because we don't understand why actually the luminosities which are quoted, which are needed, are so high. But again, here what you see, which is actually very nice, so that is a comparison of the U quark, the D quark, and the gluon, again, as function of X, and with a focus here on the high X region, where the uncertainties are still very large also, and that is also the region which is most important if you do BSM searches at high masses, then you're sensitive actually to the pattern distribution functions like very high X. So that is the baseline here, and then what Alberto did is they used the relative errors here between their own fit, including pseudodata. They include normal inclusive DIS and neutron DIS, and you see the reduction, but they needed 100 inverse femtobarn. And that is an enormous amount of luminosity. And actually, also to keep the systematics stable, they haven't done a check for that luminosity for the systematics on the data, which will impact actually your fits, is not clear. So we were thinking it might be a good idea, and there are more studies in progress, and I will show the first one. And it comes also back to a question which I will have at the end. What is actually the best observable to constrain high-edge PDFs? Maybe it is not inclusive DIS, and I will show some. So they have done work. They also have started to do an energy scan where they then have 10 inverse femtobarn to see whether, because of course you kind of have some different x, q square and y if you vary your energy, but that is their result right now. And you see that you already have quite some significant reduction. Okay, so if we think about particularly sequarks in DIS, how do we access them? We have CDIS. Of course, if we have CDIS, we have always the complications that we need also fragmentation, which then automatically goes into what Nobu is doing, that he tries to, and he will talk about later, fit at the same moment fragmentation functions and PDF to get rid of the correlation. But also in the detector, of course, it is kind of demanding because you need particle ID detectors over a really wide range in rapidity. Then we have charge current, which is actually very nice because you have a direct flavor, access to the flavor. You don't need fragmentation functions, so it is actually a very nice complementary check to see this. And I think that, but if you, for the detector, you need large rapidity and you need large squareness. I will show this. Without large squareness, charge current is not appropriate at ERC.
You need detector coverage.
Yes, to 4, exactly. Yes, exactly. I will not go into detector coverage because at the end it's an INT, not an INE, Experimental Institute. So, but that are things, and we have done studies on this. And then we have chats, and we heard a lot about this yesterday. And actually, we want to look into some of this already also at RIC. Actually, by attacking, and I will show one example, by tagging through hadrons in the substructure of the chat, actually was you can tag on what the flavor of the quark was, which initiated the chat. And again, you need large rapidity, and of course, if you do particle hadron identification inside the chat, you need also good PID. But so you have different probes which are complementary, which is always good because that will reduce your systematics, which is actually something very important in system if you want to use it. So, so W exchange. As I said, we have direct access to the quark flavor, which is actually really nice. And in the helicity case, because it's parity violating, you also have a direct case into the pattern helicity. And we saw the nice data, really beautiful data from RIC. So if you have a lepton beam, you do a W minus exchange, which makes you directly sensitive to U and D bar. If you would have a neutron target and a lepton beam, you get D and U bar. So you get actually a good access to the light flavors inside the proton. Again, complementary to see this, very high Q squares, Q square bigger than 100. If you want to have a neutron target, you need either unpolarized or polarized deuterium and or helium-3. And you can do spectator tagging. And that is just to give people an idea of how the momenta and the angle of the spectator protons are looking like. So they have roughly the beam energy, a little bit smeared because of the binding energies which you boost. And you have to have instrumentation which goes below 2 milliwatt. And for the helium-3, exactly the same thing. Okay, so that is something which you have to include in your detector design if you want to do this. So then here, actually the kinematic coverage. So here I have the inclusive lines for different square root S for EIC 45, 63, and 141. Here is actually the coverage here ahead for charge current. And then what you see here, the red dots, is the coverage we can have for charge current events for a machine with 20 on 250. So you see very nicely you cover bigger than 100 in Q square, and you come up to 10,000 in Q square. And you cover actually quite a reasonable wide range in X, from very high X to something like 10 to the minus 2. So that is exactly the region where we have big uncertainties on the PDFs. And then here you see actually also an interesting plot. That is a cross-section, depending on how it goes, as function of square root S, when you have different Q square mins. So if you start at 10, 100, or 1,000, and you see how the cross-section develops. And 100 actually is a kind of a nice compromise to start, because that gives you a good coverage also inside your detector to do this Jack-Blondel method, which you need to reconstruct your X in Q square, because remember, you don't have the lepton in charge current. You get the neutrino, which you of course cannot detect. So you have to reconstruct your kinematics all from the final state. So just to give you a little bit of a feeling, but the EIC coverage actually for charge current is nice. You see here actually the HERA cross-section, and it's roughly a factor, depending on where you sit in square root S, you lose a factor of 2 to 3. And because of the high luminosity, which we have at an EIC, we can easily kind of compensate for this loss in cross-section. Okay, so the opportunities, we can test the models on helicity retention, so whether delta D goes to 1, charge symmetry violation. We can do a precision test on handiness, which HERA also did measuring charge current cross sections as a function of the polarization. And of course, we can take also charm in coincidence with charge current to get to delta S. And unpolarized high X quark PDFs, weak neutral current couplings are constrained, something which actually has been, they are not very well known, and an EIC could do very nice work on this one as well. It's something which we have on our list, and it's the same as in the unpolarized case. Of course, you can do this. And of course, you could also do charge current in EA, but that is not the topic for here, where you can also do some really interesting kind of physics.
So we can charge symmetry as 10 to the minus 20 or 26.
So that depends a lot whom you ask. If I talk with people like Ian and some other people, then especially in the EA case, they think that could be one of the explanations for the EMC effect. So it depends.
So we call it the same thing. This is systematic charge symmetry.
Between U and D, what I mean is that U and D quarks, that is really isospin. Did I say something else?
You said charge.
Oh, I'm sorry. I'm
wow,
sorry.
that would be great if we can measure.
I'm sorry.
Yeah,
no.
Charge is charge.
No, yeah, I mean the isospin.
Yeah.
I'm sorry. I'm sorry. I should correct.
It's going to be this precise, yes.
Yeah.
Well, that would be great.
So what we did is we generated 10 inverse 5 to 1 worth of EP charge current events with Django, which is a generator which was also used a lot for HERA, and we have of course fully valid that it reproduces the HERA data, which it does very nicely. And we did 20 on 250. We use XFitter, which is a little bit of a learning curve to get that all set up and so on, but now it works. It is on, we have done also first fits, which I will show. And we have used this to first actually predict what XFitter would tell us for the observable. So you see here EP for charge current events in an EIC detector with a coverage in morbidity up to 4, full reconstruction of the variables through the Jack-Blondel method. And you see here the prediction of the theory compared with the data points which we have. And you see very nice agreement between what the data and what the theory prediction is. So that is nice. That means you can take your data and actually fit. And that is what we have been doing. And somehow XFitter uses some different parameterizations for how I would fit the PDFs, but that's okay. So they have this big U, which is U plus C, D, and then a U bar, big U bar. So it's combinations, and then your balance would be this minus that and here. And as expected, of course, you see an enormous impact on what is your D bar. So that is before the HERA, so that is a world basically that is the knowledge which we have right now on D bar with the uncertainty. And then that is if we include into the fit the EIC data. So you get an enormous reduction at high X, and that is also what you expect. Very precise data at the right X range, sensitivity, flavor sensitivity through the charge exchange, and perfect. Then we were first a little bit discouraged here about what actually is equivalent to the valence. But keep in mind, here you have a scale from 1 to 1.6 and here from 1 to 0.2. So actually you have to plot a bit better. And that's what we have done here. So actually you have to expand the range and really see what it, let me just finish the sentence. And then you see that also for the U valence, actually you get quite some, and here I actually plot the U valence, you get quite some contribution as well. Not as strong as I would have thought, but okay, maybe it is relative, I still have to calculate relative reduction, and maybe it's actually the same as here. What I am surprised, and I don't yet understand, is that we also see an impact on the U bar, and that is something which I need to, which is the combination out of U and, but it could be how it shifts things around, how the relative, by constraining one thing, you also have a relative constraint to the other one because of the relations between the PDFs and the different kind of parameters which are, but I haven't yet fully understood this. So I cannot give an answer to this. No, sorry.
That's is fit into EFXs.
That fit includes all the EP existing data.
So it doesn't include
Uh,
so fairly out.
Probably not. Probably
I
not.
think you know it might be misleading saying but without not including the young data.
Yeah, but that gives you the. So I have to check. I don't think so right now, but we can include all the data. So it,
Right.
we can do this.
Because I know that here PDFs only include.
Yes, but XFitter can do different things than HERA PDF.
Okay, that's why I'm asking.
So exactly. So the XFitter can do the Atlas W data, which needs to be included and as well, but they sit at lower X actually. So with XFitter, you can do whatever you want. You don't have to follow HERA. That is not the final word. I just wanted to show that charge current is really, and whether the reduction is from 1.6 to 1.1, or it's 1.4, the original, but I don't think the Drell-Young data constraints this high X.
It has, I mean, the U bar, the U bar minus D bar.
Yeah, but they don't have their data. Remember the big error bars which it has at the high X? I'm not quite sure how well it really constrains. But your point is well taken. Also, all data has to be included. I completely get it. So that's why I say very promising first result and not final result. It's just actually just to show that EIC can really do something. So
in it all, right?
yes, yes.
And
yes.
okay.
Yes.
So at very, very high X, that would probably be more.
Yeah.
Would be interesting.
Yes. Exactly. So I hope that with the working group which we have with Sven is also that he can participate a little bit, because some of the theory is so far above my head. So I need somebody who helps us a bit with exactly this type of things and understanding. No, absolutely. Okay, good. Then I just wanted to show that some study which nobody at EIC has looked at, but it's actually also interesting. So that are the vector and axial vector with neutral current couplings for the different quarks. And I show here actually, and I think that is still correct, that comes out of the LHEC proposal, actually. So that is the world data which we have from H1 through some lab electroweak fit, some D0. And the red point is what an LHEC could do. So they would shrink that enormously. And here is actually where the standard model sits. So if you have that high precision and you can measure that, it's actually a very interesting test on the standard model parameters also. And with all the neutral carbon and charged carbon cross sections which we can measure at an EIC, I think we can make actually a really nice test of the axial and vector couplings of the quarks, the light quarks. And that's something which I think with the PDF, it's something which we should look into how well we can do. But as I say, that is an idea. We haven't looked in anything. Okay, then CDIS. What can CDIS actually teach us at an EIC? So with Charlotte, Ignacio, Rodolfo, we have been starting in looking into what CDIS can tell us on PDFs and what CDIS can tell us on fragmentation. And by doing so, we have also started to do and define the requirements, what you need for a PID detector. Because we always have this really large requirements on things, but the question is, do you need this for the physics? So we will have some chapter, and I will not go into detail here, on actually what are the PID requirements if you want to use CDIS for different fits on unpolarized, polarized, and also for TMD. So that is something which we are working with Alexei and Noble. We want to do fits on this equivalent also for TMDs. So what you see here is the cross section in bins of X. Colors are Q square, and the columns here, so the different panels are different C. And the total integrated luminosity is 10 inverse femtobarn. We have done a cut starting bigger than 1 GV. The normal Y range, at least the minimum W cut, which is easily fulfilled at an EIC. It's not a big deal. And we require PT bigger than 200 MeV. Because if you have a magnet, and we all talk about a magnet of 1.5 Tesla or more, you cannot go much lower in PT because your particles start doing cis in your magnet, so you don't see them. So it has already cis, and so that is the X Q square C coverage you get actually for running 5 on 100. And then, of course, because we always study the energy dependence, if you go then with 20 on 250, what happens is that you get to higher Q square and you fill in, of course, the lower X region. So there's no big mystery of anything which is happening. It's just really nice. What is nice is you have actually a wide coverage in X and Q square with the data. So you can now look into what can you do with them. So, and that is what we have been started as well. And now bear a little bit with me because it is different plots which you maybe haven't seen yet. So we have used the reweighting method to define the EIC CDIS impact on collinear unpolarized PDFs and also on the fragmentation functions. So what if you do this and we follow basically the NNPDF kind of method, we have the replicas and we have many replicas. So we have thousands and more. Because if you want to do this high precision reweighting, and no one knows it much better than I, because he does this type of things, you need actually a large set of replicas because you will have very small uncertainties and you can kind of get funny results if you don't have enough of them. So we have many because we work also with the NNPDF, and then you can kind of define these correlation functions, which is the correlation between your observables and your flavor. And you could plot these rows, but we have actually kind of done something a little bit further. We have also to take into account to visualize this better where the data has actually impact. We kind of take into account by normalizing this correlation factor with what actually your experimental uncertainty is over the uncertainty of the PDF to your observable. Roughly clear? Okay. And then you get this S. And now here what you see is actually you have then so you see this normalized correlation function for the S, the S bar, the U bar, the D, there's a typo, and the D bar as function of X and Q squared. And where you have big bumps, that's a high correlation, so you will constrain things very well. And where you have smaller ones, the things are already very well determined. So that is for pions. And of course, pions wouldn't have so much impact on strangeness because that doesn't work. And that is for 45 GeV. So then we have done, but what you see is that the correlation to U and U bar and also D and D bar is actually larger. Okay, so then we do the same thing at 140 GeV, and you see that actually the kinematic region moves, and where you get actually kind of constraints also kind of becomes larger, and that becomes also because you have bigger Q square lever arms to fit it. The same for kaons. Of course, immediately you see the kaons make more impact on the strangeness. And the same for the 140. So you see big blobs at certain areas is big constraint. Of course, I can show you to you also a little bit more digestible. So that is actually really the fit. So the NNPDF, and then after reweighting, for again a square S of 45, so that is U, U bar, D, and D bar, and you see nicely that you constrain actually already at that square root S, U bar on the D and the D bar as well, and even on the U. And then actually, if you take the higher square root S data, you see that the uncertainties even shrink further. What you see, and what we don't yet fully understand is that, and it has probably to do still with the 10 inverse van der Waals, your uncertainty at high X for CDs are large. So CDs is probably not the tool to constrain high X PDFs. And it might also have to do with the correlation with the fragmentation functions. We are not doing a combined fit. It could be better, but what you can definitely see, there's impressive impact, and I show you one more which has impressive impact for the light quarks at the smaller X, so X smaller than 0.1, and the impact grows with square root S. So if you have the full energy range, it grows. So then here is the impact on the kaon, from the kaons on the strangeness, and that is of course enormous. So here that is S plus S bar. So you see that is on the ratio, and we haven't released any kind of correlation, so that is less. And then it becomes even more if you go to the high square root S. So the impact of CD's data on strangeness, which is not a surprise, we know that already, because you have inclusive, you have very little chance to have anything which is sensitive to really to strangeness apart from neutrino data. And the neutrino data will never reach this low X. So the EIC will make an enormous, if we can get CDs included into fits, and the groups are working on this, an enormous impact on strangeness. So, last on this topic, and here I don't have yet impact fits, but we use exactly the same method as for the PDFs for the fragmentation functions. And here you see actually the singlet, so that you have quark plus antiquark to hadron, which are specified. In pink we have the kaons, in blue we have the pions, and you see that as function of C and then as Q squared. So you see again, kaons of course make quite some impact on S, U bar. And then you have the D bar here, U bar, and so on. So again, also there, the data will make a large impact on the fragmentation function. And of course, if we can fit the singlet, we can do also the non-singlet, so the quark minus anti-quark, and also there you see the same. I cannot show you yet reductions in the bands on the fragmentation uncertainties, but yeah. that is what we have on this. So then I want to just use one example for jet physics to determine PDFs, and in that case unpolarized and polarized PDFs in a photon. And Brian talked about this already. So we did a simulation of dye jets in the photon production regime, so a small Q square, where you have this point-like contribution and then the resolved contribution of the photon. The dye jets can reconstruct very nicely the X inside the photon, so that is the generated versus the reconstructed, so you see very nice, and here you see projected. So if you do a cut on X reconstructed, you can definitely enhance your resolved. And that is a method which was also used at HERA. So that is actually just to show that is the unpolarized cross-section which we can measure as function of basically something like the dye jet mass, and here as function for different X regions. So you see very nice precision, and that is only for one inverse femtobarn, and that is the same, that is for the polarized one, and ERC would be the only machine who can measure this, and that is actually critical input if an ILC is realized in a gamma-gamma option, because they need the polarized photon PDF, so very critically for some of the physics. Okay, what we have been doing then, we went one step further and identified actually hadrons in the jet, pions, kaons, pi minus, and k minus, and did a PT cut, so basically looking to how leading this hadron is, and then did a check on if it is a pi plus, how you can enhance the fractions, and it is a U bar. For the kaons, and you see you enhance S if you have k plus or k minus. So that could be, if you provide that, that is also something which Lab already did with their text kind of things. You can enhance actually what the flavor structure is inside the fit. What actually would be really great is if the PDF fitters would do an update on the photon PDFs. LHPDF has even removed them from their overall kind of distribution, because the fits are so old, they don't include the lab and the HERA data, everything is before. And actually, if you want to do some of these impact studies, and there's also some other interesting physics why you want to have photon PDFs, which has to do with astrophysics, it's very difficult because you don't have any uncertainty events. So it would be actually really nice if there could be some collaboration to do this together. So what else can be done? And I think it is like simply a last crusade. It is a hint for the holy grail in spin physics to resolve the spin sum rules and decompose actually what the different components are for the spin of the proton. So why should we care? We all know spin is the least known quantity which we have. Depending on what model you have, actually there are not a lot of models which predict really some of the spin decomposition, but if you have pion and kaon cloud models, actually what it would mean is that your C-quarks should be unpolarized. So that is actually some kind of an interesting test. You have some chiral quark soliton models which predict actually how the imbalance between U bar and D bar is, and we have the unpolarized, the helicity, and then the question is also the transverse, and what would we see? And can one of these models actually predict all of this? Because that is really non-perturbative physics which leads to this. And of course, we can kind of, some of this can be very kind of, if we have high precision data, we provide very stringent tests to lattice and can kind of have complementary information and see what we can learn by combining the information. So we saw yesterday already, based on the RIC data, there is actually the first indication, or it's more than an indication, that the gluons contribute to the spin of the proton, so that it is not all a quark object. But of course, the uncertainties are still very large, especially at low X, and that is actually a plot from the NNPDF. the red is before the RIG data were included, and then green is after. And what they included right now is mainly the star chat data. The pion data from Phoenix have not been included because they didn't have their own fragmentation functions, but they are working on doing this. So then something which Werner said also already, some of it yesterday. So that is actually the region which was constrained by the integral. So here you see the value, the Quaisure distribution. And then if you look how that actually develops by changing Q square, going from low to high Q square, you see it becomes wider, but also that actually your value kind of shifts if you integrate over a fixed region. And that mainly comes from the fact that if you kind of evolve in Q square, your distribution, if you compare it to the RIG range, which is kind of here, that your main peak, where the gluon peaks actually walks at higher Q square to a lower X. So that is kind of why you get different values, and it also shows that the integration over which you do that is important. So why is actually separating flavors important? I gave already some of the arguments, and one of them for sure is we want to see what the imbalance between U and D bar is and strangeness. But also if you look right now, and that is a running integral over the quarks, as depending on what your X min is, for DSSV 2014, so with the data which were included at that moment, which is basically also world data apart from some of the latest RIG data, but the RIG data is not so relevant for the quarks. So you see actually that in the measured region where you have data, the contribution of the quarks is 0.36 and then 1/2. And if you kind of go down to 0, because it kind of never saturates the contribution of the quarks, you always get a smaller and smaller value. And the reason for this, at least it's something which, and Werner can correct me, what we were discussing with Marco and Rodolfo, is the contribution of the strange. The data which we have right now is not enough to release all these constraints like this 3F minus D and so on. Whether they are actually applicable to doing fits at a high Q square, because that is actually really low scale, and how you transfer this to where we do the fits is not so obvious. And we had a very nice talk at the last INT in 2010 by Michael Lavage, where he was actually talking about this and making the point that maybe we should kind of not do this and take this out. But right now, we cannot do, which actually forces and also causes this puzzle between inclusive and CDS data, that if you have inclusive data, which of course have no sensitivity on strangeness, you get this shape which is negative to fulfill your parameters here. And the CDS where you have data in the region, you get a slightly positive kind of strangeness distribution for polarization. And in 2 sigma, everything is consistent, but it is a question how actually goes the low X behavior. So the EIC compared to the world data which we have here, that is a fixed target, that is actually the RIG data, the chats, and that is the W, can extend in X and in Q square actually always 2 decades at a fixed X and at a fixed Q square. So we will get an enormous increase in statistical power if we populate this. So for the spin of the proton, if you look right now and you say, okay, my gluon is roughly 40%, my quark is 30%, I know it has to be 1/2. I don't think anybody debates that the spin of the proton is 1/2. So I could be naive, and I just subtract it to get the orbital angular momentum. And if you look to the current data, you have absolutely no constraint. You cannot do this. So you don't know what this LQ and LG are if from measuring the gluon and the quark precise. So one of the things, despite that we maybe can measure these guys differently, which comes back to my questions later, one way would be to measure the quarks and the gluons really precise and then do a subtraction. Okay, the way to measure is to measure the G1 structure function, which is the difference between having a quark anti-aligned minus a quark aligned with the spin of the proton. If you take the integral over the quarks, you get your quarks, and you get the derivative, like in the unpolarized case, gives you the delta G. That is how actually at the moment G1 looks based on the uncertainties from what we have from the PDFs as function of x and a fixed q squared. So here is a central value, so it goes to 0. But we, starting from 10 to the minus 2 on, we don't even know anymore the derivative. That is actually, if I put in the data from an EIC compared to the uncertainty bands, and you see that actually they will definitely tell you in which direction it goes and what the value is. But one thing actually to this discussion yesterday, if you don't go lower than 10 to the minus 3, you basically tickle only a little bit this region where you get this large kind of difference. So that is what we have been doing. We have been simulating all of this for different square root s, which are the different colors here, as function of q squared x, so the same like the Hera plot, the scaling violation plot. That is where the fixed target data sit. So it's clear they will not help you in addressing where the big uncertainties are. So the blue bands are the uncertainties based on the current world data knowledge on the polarized fits. So what you see here also, so that is actually plotted the derivative, and you see that if you have the smallest 20 to 250, then you go into the region where you have the biggest uncertainties, and you need always 2 points to make a fit. And if you have a square root s of 70 and smaller, then you would only access here. Okay, so then we have also looked in how well we can constrain the sum rule. So here, that is 1/2 minus the quarks and the gluons if I stay in this region 10 to the minus 3 to 1. So that is what the uncertainty is, and that is what still sits at the region below 10 to the minus 3. So if I do that to 10 to the minus 3 with an EIC with this precision, including also the fixed target data, that is what I get. And I claim that is not a decomposition of the spin. That is what we have right now. Then I add more. I go up to 40 to 70. And you see, because you kind of populate regions, especially higher Q square regions and regions where you have big uncertainties, you shrink this. And if you take actually the full square root, then that is in this PDFs, of course, that is what you will get. So you will, if you have a full EIC, you will measure the full spin decomposition.
Just for clarification,
yeah.
The quarks do contain this factor 1/2, right?
Yes, absolutely. So if you then do the same trick, that is a running integral for the gluons, that is a one for the quarks, and then you can actually subtract and you get a constraint once you orbit range. That is how well you can constrain actually the different flavors that you have here. This funny behavior for the strangeness comes exactly from this constraint of the 3f minus e, which forces it artificially to give small uncertainties. And that is how well you would do on u bar minus d bar. So the last one is polarized charge current. We have a long time ago already published a paper on this. You see here the cross-section, which you have for different things. We have done proton and neutron by doing a neutron target. That is actually the polarized cross-section. That is the structure functions which you define. And that is how well you would constrain actually the light C-quarks from this. So that brings me actually to my summary. More work absolutely has to be done on the polarized and sector for PDFs and fragmentation functions. But I think an EIC will be critical to further our understanding on PDFs and fragmentation functions. I did not discuss inclusive TIS and F2 charm. But the coverage, we have done that study for nuclear PDFs, and the coverage will be much better because we have a larger reach in X and Q squared than our study here. High square root s is the only machine to unravel the different components of the spin of the proton, and especially critical to the low X behavior, which we will hear from Yuri. Charge current is an absolutely important observable to flavor separate and test limitations of CDs. And here come my questions by looking to this. And yesterday, we already heard about the neutron target, this question deuterium versus helium-3. If you have a proton machine which can do 250 GeV, then your deuterium maximum energy will be 100 GeV, and for helium-3 it will be 166. It has to do with the rigidity of a beam in a machine. You cannot overcome this. So for a deuterium, you will have only half of the kinematic coverage than you have for protons. So the question is, what is it you want? I would actually even challenge, do we need neutrons for some of the things? Or can we do that with actually charge current and the proton only? But that is a study which needs to be done. But what needs to come from the theorists actually, what is the better choice with respect to nuclear effects between deuterium and helium-3? I have no idea. For the high-X PDFs, I think I would really like to understand what are actually the limiting theoretical factors to determine high-X PDFs. Are there, even if I'm at a Q-square of 100, is there still some issue with higher twist? I don't think so, but what are the limiting factors? And what is the golden observable to constrain that should the gluon at high-X? I think it is F2 charm and FL charm, and maybe an FL measurement, but I don't think you can get it from the inclusive type of things, because it's just the precision would be. Then actually, so I have listened, but I haven't yet heard how we measure LQ and LG from the Jeffrey Manahan. Because there's also, and I would really like to know this, because then I can look whether we can do this. And then actually following our discussion from yesterday also, we definitely can make contributions to understanding fragmentation functions. But that is not the same as hadronization. And again, the question would be, what are the golden observables to learn about hadronization? Do we need correlation measurements between different rapidity ranges, forward, backward, and things like that? Distributions inside the jets? So would be nice to kind of clarify these questions, because I think that would actually really bring us also forward in our what we want to write up for a further white paper. Thank you.
So concerning the question whether we need neutrons or not, I guess probably your studies would be at the moment the best way of answering that. I mean, you have neutron results for the charge current, right? Mm-hmm. And so they do seem to have impact, right?
Yes. 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 Yes.
So you say you didn't do this study of the EIS. My question is.
This one here?
Right. So my question is regarding the strength. I know that there is observable parity in the EIS, which is very, in principle, constraint distribution. I know that there are some people who did this study. My question is, where is the status? Is it
which one? You mean W with charm?
Is the gamma is the interference stem in polarized electron beam or a non-polarized target? If you do make the asymmetry, you will get the gamma's interference, which gives a different combination of the photons, access to the strange. The question that I have is, what is the status of that? Is that completely hopeless relative to this status?
You are the first one, so I say what.
No,
go ahead.
I don't want to.
No, go ahead. No, go ahead.
So, I mean, there is this relatively old work, but my understanding is that to truly get to the constraints on the first moment, delta S, in the end, what you need, in addition to parity violation experiments that have been done in China, are measurements of elastic neutrino proton scattering. There are at least two older measurements at Brookhaven. I'm tempted to say one of them was EA34, but there I would need to check the number. Well, issue is a big word, but let's say a critical concern we should have with that is that those measurements went through reanalysis that actually shifted them quite a bit. I do know that at this point at Fermilab, folks are looking at trying to repeat this with a different type of measurement technique, where you would actually truly observe the neutrino interaction itself, as opposed to one of those massive targets where you just wonder whatever afterwards. I have, however, not seen, let's say, a clear projection of uncertainties there at this point. That may be because I didn't look long enough in the end. May also be because it just hasn't been really estimated.
So Krishna Kumar did something at the beginning, and I know about this. And the problem with the gamma C interference absolutely is a tool which you can use. But the gamma C interference, to use it, sits up here. You need extremely high Q square to do this, because before you have single gamma exchange, or you have the W exchange, and the gamma C interference sits at a Q square bigger than 1,000, something like this. You can look for Hera. Hera has measured gamma C interference, and the asymmetries will be small. So it's an extremely challenging measurement. It has sensitivity. I'm not debating this to strangeness. I don't think you will ever reach something which is comparable, which you can do with CDs, or you can do with W with charm. Because the kinematic reach which you have, especially not the momentum, is here. And we all know that if we measure only at this region, your extrapolation to the momentum is to the integral is enormous. So it's very nice observable, again as a complementary check, I think, but I don't think you will get the integral for delta x. Go ahead.
Okay, so can you go back to the orbital angular momentum as a function of x minimal?
Wait, no, the one which after ES.
Yeah.
Yeah.
Yeah, so it's integrated from 1 to x minimum, right?
Yes, exactly.
So,
and of course,
so
it assumes the DSSV. So the central curve is in that model. Don't take that.
So if you take a derivative with respect to x minimum like delta x, this is x distribution for the sum of the plot and the zone.
Probably, yes.
Okay, well, I'm very much interested to see that. But so that means that you have a constraint on that even at large x.
Yeah, because what happens is it's the x min, so you have a very, so you don't have a constraint on the how should I say, on the integral. For that you need to. So that is the difference here. So that is basically you subtract the delta sigma, the delta g, and you see the 1/2 is there. and you get this. So you have. If you have only this, you would anticipate that you have a lot of orbital angular momentum, and you see it only saturates in this model if it becomes flat. The same as for the gluon and for the delta sigma, we have the problem which I discussed because we have these constraints. So I don't think you can say, I think the region where you can say is that you have measured the integral values if all of these three are kind of getting flat, because then you have not anymore a large contribution from the small c, and that is in the order of, in that model, 10 to the minus 4.
No, but I think you cannot, I mean, it makes little sense to go at high x, right? Because there is no sum rule at high x. I mean, it only works after integration, right?
Yeah.
Down to 0.
So this plot, I think, is a little misleading in some sense.
It doesn't work for any finite.
I mean, if you look at 10 to the minus 2 or something, there would be literally no statement you could make on anything related to orbital angular momentum, because you know, it's just not.
Yes, yeah. In fact,
I think this plot is not good actually. It will really,
in this context, in this context, after that,
I think that this is a way to start looking at it, and that's great. We're starting looking at it, but I think that what is missing there is the information from computers exclusive experiments and one.
That is
Number
not the
two.
same angular momentum. I still don't understand how I can use anything
Well,
from
then why do we write
exclusive.
the papers for? I mean, okay. Anyway, so we explained that how they connected to it. In any case, aside from the theoretical issue, okay, now, one can insert, this is the ideal place, even more so than for the tensor charge. This exercise has been done by Weiwen, who's not here. It's the ideal place where we should think about how to insert information from the lattice. Because, yeah, so we should
I
start
can
thinking in that
insert.
sense.
So I know about your papers, and I know about the papers about this twist-3, DVCS, and I have written the only paper on DVCS on EIC, if I may say, which we did all the studies, which we did an experimental study on all of this. So I know about this. But there are also other papers which tell me I cannot use this twist-3 to measure this LQ and LG. So I am, as a simple experimentalist, and that's my mistake, that I'm not a theorist, I don't understand actually how to measure it. There are conflicting information, and that's why I asked on my last slide, what is the golden observable to get a handle on this? And I'm still confused.
Okay,
What's the golden
so I think that
observable?
Brandon's going to talk a little bit about the observables.
Good. Exactly. So that's why I put it this question: what to do?
Yeah. Okay, but the point was, here is where we can get guidance from lattice. Even more so for the tensor charge, we almost got it compared to this. But, so an exercise that she did, yeah.
I'm not saying that we cannot put in different things, but if I want to do it only experimentally, without putting things in which might have a completely, for example, I wouldn't know so easily how I put in lattice, which has a different systematics in that study, which I'm happy to do. I'm not saying that we shouldn't do this, but if I do it experimentally, I'm not yet clear how I measure this LQLG. And I'm happy to hear observables, and I'm even happy to simulate the data for this. So,
let me turn this around a little. Suppose there is a clear connection between this three GPDs and this orbital momentum. Is there a handle on this three GPDs? I mean, these extensive studies, of course, you know, the leading twist primarily, but then I don't know, Q-squared dependence or so.
that is exactly the thing. So, the studies which we did already measuring. So you never measure GPD. So there we already go. We measure maybe a cross section and an asymmetry in a certain region in X and Q square and psi, and then you have to extract the GPD, which already for the normal ones is complicated. So now for the twist 3, I have no idea how big the extrapolation region is. And it is probably more complicated, but somebody with much more knowledge can talk about this. So I personally don't know how big the systematics is that you measure in a small region and you have to extrapolate to all this X on the light cone, psi not equals X, and all this type of things which are there. So I think that would be actually a very interesting study to once do and say, okay, I measure in this region, how well is the extrapolation?
Yeah, so I have an X distribution for the orbital angular momentum, which is just these two parts with the 1-0 recheck, and this 3 part with the genuine 3 parts, and that is related to the Wigner distribution. And so maybe you don't agree, but I have an X distribution.
Right, no, that's fine.
That's a twist-free PDF. It's like a twist-free PDF, and that's related to the Wigner distribution function. And so Shandong, G, and Penn, and they propose how to measure it using the single spin asymmetry in digest production. But it's a very complicated convolution, and I don't know if it's, and I think the calculation is not finished yet.
No, I mean, I
To
didn't
me-
mean to
to
say,
me-
I didn't mean to say anything against that at all. I just said the plot on the right. This
Oh, yeah,
is
this one is
Yes.
saying that
you're subtracting a full integral to subtract
Yes.
from it running integrals. You
Exactly.
Can't make any.
Yes,
And not sorry against you.
yeah.
that is true because I have a thing and I should maybe not have it as X.
So,
Yes,
so there are observable proposed for to measure this canonical orbital moment.
Yeah.
Here, it's there's a paper by Andreas Metz and his collaborators. That is not the EP. It's from.
Still, it's very low X, right?
That's pi. What's
Kilo X.
It's without heavy cognitive.
J5 reduction,
There
yes.
are a couple of proposals, but
To me,
they're all very difficult to measure.
Are you going to talk about that tomorrow?
Not that.
So I think it would be really good if we could come to a kind of consensus in some way, what the way is to measure something.
we had those analogous papers to that, and I guess Alva's gonna talk about it. And we made the connection, so there was a suggestion, there was, so the twist reconnection was made long ago by Polakov and then in the theoretical context by Yoshi. And, but what we did, and we allow the experimental analysis, is to connect the GTMD to the twist piece. Now, I don't think that one should even go and think about measuring the GTMD at this point, because that is really difficult. I mean, there are suggestions, as Yoshi is saying, but that is really difficult. It's the quantity that is way more accessible is the twist 3GPD, rather than going to an integral of a GTMD. That's what I'm saying. So, but an integral is important because it allows us to connect with the lattice, it allows us to define it theoretically. But I don't think it should, I don't think that one should go out and measure the specific GTMD. I mean,
This 3GPD doesn't help because we don't have enough observer to get the G2. We want the G2 for the 3GPD and we don't have the observer for that because it mixes with another one. That's the
No,
issue.
okay, you haven't looked carefully enough.
Can I make
Brandon's
stop,
gonna
stop.
show something.
I don't want to cut off anybody. On the contrary, I want to make a suggestion. That's a very interesting discussion, and I wanted to suggest that we meet this afternoon at 2:30 to discuss this. Because I think we want to hear Nobu, absolutely, I definitely, and everybody else probably as well. So, and it's probably, it's a long discussion, and I think we should really have this because it is very relevant. So is 2:30 a good time for everybody to meet in the room next door or here, and we have a discussion about this? I really don't want to cut off anybody. It's on the contrary, I want to extend it. Okay, so I think we move on to Nobu.